Let's look at one more example. Say that engineers at OU's Advanced Radar Research Center are comparing a standard radar design to a new radar design they are developing. To compare these two radars, the engineers collect the radar detection distances in miles for 15 common targets. We want to know if the new radar can detect targets at a greater distance relative to the standard system. Okay, so we've got 15 observations, and these are the same targets. Okay, and we are determining how far away the current radar can detect this target relative to the new design. Okay, so here's the new design for the same target. Okay, so we've got one measurement on the same target and another measurement on the same target. So these two populations are dependent on each other. Okay, so we have to use a matched sample, paired sample, something like that. We have to use an approach for comparing the difference in means whenever the two populations are dependent on each other. Okay, and so we can go and find the differences, the d sub i's of each one of these for each radar for each target. Okay, so how much better or how much farther away can this design detect this object from this design? That's what this difference means. Okay, and we want to know, is the new design better than the old design? Okay, is the new design better than the old design? So if it's better, that means that it can detect the image, the target, farther away. Okay, so we would want this number to be bigger than this number. Okay, if the new design is better, this number should be bigger than this number, because this number, or this radar would say we're detecting from farther away, bigger number than this one. Okay, so we want to know, is mu sub d, the mean difference, is it less than 0? Okay, is the mean difference this minus this, is it less than 0? If it's a negative number, that must mean that this number bigger than this number. That's what we want to detect. Is this number bigger than this number? Can we detect images from farther away using the newer design relative to the current radar system? Okay, so we want to know, is the mean of differences negative? And since we're saying strictly less than 0, that must mean that we're talking about the alternative hypothesis, because, say it with me, equality must be in the null. Okay, so here's our equality statement in the null hypothesis. So all we have to do is just go calculate a test statistic that is d bar minus mu sub d all over s sub d over root n. Okay, so we've got to go find the d bar here, the average of the differences, d bar in this case, for this sample of n equals 15. That difference, average difference, is negative 0.349 miles. And the standard deviation for those differences is 1.37. Okay? N equals 15, that suggests that degrees of freedom is 15 minus 1, or 14. Okay, so we just plug these numbers into here. Negative 0.349 minus 0, okay, divided by S sub d, 1.37 over root 15. Okay, if we do that calculation, we should get a value of negative 0.987. Okay, so our test statistic, negative 0.987. And let's take a look at the p-value approach. Okay, p-value approach using just the table. So we have degrees of freedom 14. We go down to the row associated with degrees of freedom 14. And we want to find the p-value, the lower tail, okay, below negative 0.987. We want to find this area. That is the p-value. So we go down to row degrees of freedom 14, and we kind of look around at those values and see if we find something close to 0.987. The closest we get, the smallest value on the axis that we get for degrees of freedom 14 is for 0.1 in the tail. Okay, that is 1.345. Okay, 0.1 in the tail, or let's just say if we want it down here, that would be negative 1.345. And that's the largest area that we can find, 0.1 in the tail. That's the smallest value of t that we can find in the table. Okay? Our t value is still smaller than that. So that suggests that our p-value is greater than 0.1. Okay? We don't know exactly what it is, but we know that it must be bigger than 0.1. And technically, we know it's less than 0.5 because half of the distribution would be 0.5, and we know this is a negative number. So our p-value is between 0.1 and 0.5. That's still a pretty large p-value. Probably would not reject the null with an alpha of greater than 0.1. So we're probably not going to reject this null here. We're going to conclude that the current design and the new design roughly have the same detection distances. Okay, their differences are not less than 0. Okay, current radar minus new design is not less than 0. We could also look this up, get a little more specific value using Excel, using the t-dist function. So the p-value, if we want to use Excel, would be the t-dist function. Okay, we've got our value, 1.345, 14 degrees of freedom, and this is a one-tailed test. And if we do that, we get a p-value of 0.172. 0.172. Very large p-value, larger than any alpha we would ever choose. And again, if the p-value is larger than alpha, we do not reject the null. We're not going to reject the null here. We have no reason to believe that the new design allows us to detect these images from farther away than the current design.